Hello friends, this is Jim here with Science Talk, and in this video I want to discuss with you what is happening in the ocean, namely a lot of things happening in the ocean, but in this particular one I want to focus on what's happening as far as pH, the acidity of the ocean, and what it is doing to the marine food webs. And at the end of this video, I guess you could say the second part, or the latter part of this video, I'm going to explain to you what's meant by the what's called the CCD, calcite compensation depth. That'll be at the end. So what is happening? We're seeing the acidity of the ocean becoming more acidic, which means the pH is decreasing. This, of course, is the result of the CO2 from the being absorbed from the atmosphere from burning of the fossil fuel. CO2 plus water equals carbonic acid. Carbonic acid is a weak acid, but it still is introducing protons. We usually, pH is actually defined as the measure of the log of the concentration of protons. And protons is one of the definitions used to define acidity. The more protons you have, H+, the more acidic it will be if they outnumber the hydroxide ion, OH-. Anyway, I'm getting a little sidetracked here. So with the decreasing pH and the increasing acidity, this is affecting the food web, is affecting organisms' abilities to survive. And this could impact great stretches of the ocean as far as finding a sustainable ecosystem there. So let's look, for example, at the Southern Ocean, which is of all the open oceanic regions. Open ocean means the middle of the ocean. We're not talking necessarily coastal processes or coastal productivity and those kind of things, which is typically on-shelf processes. We're talking about in the actual open ocean. The Southern Ocean is the most productive open ocean area on the planet. Well, parts of the Southern Ocean could become impoverished as more acidic seas displace the marine life and the marine food webs that are found there. And they go on to state in this particular article here, tiny sea snails that form the basis of the food supply for one of the world's richest ecosystems could disappear because the depth at which they can form their shells will have shifted. This is the CCD, the calcite compensation depth. I said I will explain what that is at the end of this video. I want to first present to you the findings of this study. Okay, so in Antarctic waters, now of course we have the phytoplankton. The phytoplanktons, do their thing. We have zooplankton grazing on them, and we get the krills with the shrimp-like creatures. The krill helps feed all the baleen whales, and we get the fish eating that, and the fish help feed the pinniped, and the orcas feed on the pinnipeds. You get the idea. Well, there are also creatures known as pteropods. That's spelled P-T-E-R-O-P-O-D. Pteropods. And right now in Antarctic waters, they can exploit the calcium carbonate dissolved in the ocean down to a depth of 1,000 meters in order to grow their shells. In other words, as when they can go down as far as 1,000 meters, and they'll be able to take the calcite, calcium carbonate that's dissolved in the water, extract that from the water, build their shells. Below 1,000 meters, they can't do that. Well, in general, what's happening is that this depth at which they have this ability is shifting, and it's shifting upwards, closer to the surface. So there are two kinds of carbonate, calcite and aragonite. And these calcite types are going to alter due to the decreasing pH, the increasing acidity. By 2100, there will not be enough aragonite. Aragonite is the species, the kind of carbonate that most organisms favor. And that's to do with the arrangement of the atoms that make up the molecules. Right now, pteropods flourish in the top 300 meters of the ocean. By 2100, the survival zone for the pteropods will end at a depth of 83 meters, 217 meters shallower. So, in the journal Nature Climate Change, that's where this report appears, scientists warn that this could change the food-web dynamics, have cascading effects on global ocean ecosystems. In other words, the larger fish and marine mammals that feed on the smaller creatures that in turn depend on the basic diet of pteropods will have nothing to eat, which means they starve. Now, what does that mean for global fisheries? Do I really need to comment on that? We know it's going to crash the fisheries. That means this is also going to directly impact humans' ability to get food from the ocean. Now, all shelled marine creatures, whether it be the diatoms, the coccolithophorids, right, phytoplankton species, when they die, these are any creature that has producer or consumer, they have a little shell or test around them. When they die, they tend to sink to the ocean sediments, form a layer there, and then we can come back later, take a core there. We do all the isotopic ratio fractionation studies, which I've explained to you before. We do all that, find out all the information that we can, and go from there. So, you know, if you're talking diatoms, coccoliths, foraminifera, radiolarians, clams, mollusks, right? Anything like that. Corals. Let's not forget the corals. Granted, they're not in the Southern Ocean, but you know, these are creatures that have shells, some sort of deposition that the organisms themselves make, right? This is all going to be imperiled. So these organisms that form the shells, they depend on the correct levels of calcite and aragonite to form the exoskeletons. We all know the oceans cover 70% of the surface and provides the largest living space for organisms. We know that the deepest trenches are deeper than the tallest mountains. You can take Mount Everest, shove it into the Marianas Trench, and you're still going to have 4,000 or 5,000 feet above the tip of Everest before you get to the surface. So, what is happening? You know, we know that, or we strongly suspect that the oceans are where life first formed. In fact, the hypothesis is pretty much in situations similar to the present-day hydrothermal vents. And so we have the scientists from the US and Norway that chose one species with precise needs, you know, as an indicator of what the climate change is doing to the ocean. And so they chose the pteropods, because pteropods are specific in their need to form their shells. They found what they call the aragonite saturation horizon became dramatically shallower as the seas became more acidic. These calcifying organisms will struggle to build and maintain their shells as acidification proceeds. This is a quote from Nicole Lewandowski, who's associated with the University of Colorado at Boulder and one of the researchers in this study that has been published. In the future, a pocket of corrosive water will sit just below the surface, making life difficult for these communities of primarily surface-dwelling organisms. That's a quote from Dr. Lewandowski. As the world warms, acidification of the oceans becomes inevitable because of the absorption of CO2, right? CO2, water, carbonic acid, told you that earlier. Researchers have repeatedly warned that such change can only diminish ocean life, harm the coral reefs and kelp forests that shelter the rich biodiversity of sea creatures, change the behavior of fish, And I've got some videos discussing what warming oceanic waters will do to fish. I have those videos coming up, as well as certain types of shrimp, and threaten the shellfish harvest. But for the first time, scientists have been able to model the impact of atmospheric change on the ocean chemistry in one zone at precise depths. So this is an extremely invaluable, important study. They have done a great service here. The message is that right now the pteropods have plenty of sea space for survival, but the aragonite saturation horizon may have already begun to shift in some places, and perhaps it already has started as recently as 2006, or perhaps later. But once the change continues, it keeps going. Once you get the thing, especially with the oceanic situation, you know, once you get something going in the water, you get that momentum, that inertia, it's kind of hard to turn it back. If emissions were curbed tomorrow, this suddenly shallow horizon would still appear, even if possibly delayed, said Dr. Lewandowski. And that inevitably, along with lack of time for organisms to adapt, is most concerning. It's happening so fast, the organisms do not have time to adapt. So basically, what's happening is the pH is dropping, so the acidity of the ocean is increasing. The organisms won't be able to have the calcium precipitate, won't be able to pull out to precipitate to form their shells or maintain their shell. The calcium will remain dissolved. Okay. Now, so now for the rest of this video, I want to discuss with you what is meant by the calcite compensation depth. Now, this might be a bit technical, but you guys can handle it. The calcite compensation depth is also called the lysocline, Lysocline. This is like we have thermocline, pycnocline, halocline. We have the lysocline, which is a sharp change in the concentration of calcium carbonate, be it calcite or the aragonite form. So the calcite or carbonate compensation depth, sometimes in older literature you see indicated as calcium compensation depth. The idea, it's abbreviated CCD. This is the definition refers to the specific depth of the ocean at which calcium carbonate minerals dissolve in the water quicker than they can accumulate. Let me repeat that. The CCD refers to the specific depth of the ocean at which calcium carbonate minerals dissolve in the water quicker than they can accumulate. So below the CCD, the rate of dissolution exceeds the rate of precipitation. Above the CCD, it's the reverse. The rate of precipitation now exceeds the rate of dissolution. Many plankton species build shells for themselves by chemically extracting mineral material, either calcium carbonate, which is CaCO3, that's the chemical formula for it, or silica, SiO2. Diatoms they pull out silica, like you see diatoms in the Arctic Ocean. And they pull this, of course, from the seawater. Carbonate compensation depth, of course, refers only to calcium carbonate, CaCO3. It obviously does not refer to silica. That you would have the silica compensation depth. That is not as widely understood. And I'm just going to keep my remarks here to the CCD. When calcium carbonate shelled organisms die, the skeletal remains begin sinking towards the bottom of the ocean. This creates a calcareous ooze, and that's the word we use, that can, under pressure from the overlying water, form limestone or chalk. So you have two things going on here. You have increased pressure can help precipitate as well. Not everything that sinks in the sea reaches the bottom, however, because the chemistry of the ocean water changes with depth. It's kind of to be expected. Surface water, where most plankton live, is safe for shells made from calcium carbonate, whether that compound takes the form of calcite or aragonite. These minerals are almost insoluble there, which means you can readily form the shell. You can readily precipitate them. And the organisms use that principle to form their shells and maintain their shells. This is how coral reefs grow. You have the polyps excreting the material to form the reef, and it keeps building, building, and building. I mean, you can look at a big coral reef. The organisms are found in the little, what's called calyx, the calyces, plural. And the rest of it is just what we call carbonate skeleton. But right in the little polyp. And at nighttime is when the polyps will emerge their tentacles to filter feed, and that's when you'll see that. During the daytime, it's kind of, well, that's very pretty. At nighttime, the reefs will look completely different because all the polyps are sticking their tentacles out, filter feeding, and going to town. Okay, so at the surface, the minerals are almost insoluble. But the deep water is colder and under high pressure. And both of these physical factors increase the water's ability to dissolve calcium carbonate. If it were not for the pressure, then temperature would alone would determine, for the most part, solubility. Usually warmer temperatures will increase the solubility, usually. But under intense pressure, the pressure now takes over. And there are things that we can calculate what's called a solubility product constant. It's all crazy chemistry. I'm not going to go there. But it does get involved. It gets used, what you can gather from this. More important than these is a chemical factor. This is the key bit. The level of carbon dioxide in the water. Deep water collects CO2. Well, you have creatures living there, and they're respiring CO2, whether it's bacteria or fish or some other interesting life form. And we have these creatures eat the sinking of organisms through the water column. We actually call it marine snow. And it relates to that calcareous ooze, but there's organisms in there that may be dead, but there's organisms in there, and you got a lot of detritivores at death that are going to snatch those up. So, because of the higher concentration of CO2 at depth from respiration and the sinking from the surface, the water at depth is more acidic. So, what can affect solubility, or for that matter, will affect things to precipitate? Temperature. Okay, we all know that you can, if I'm dissolving, say, salt in water, okay, I can dissolve more salt if I heat up the water. Well, yes, so temperature can control solubility. And in the case of calcium, pH controls the solubility as well. So we have temperature, pH, pressure. Those are the three main factors. At depth, it's primarily pH, determined by the CO2 level, and the water pressure. Because when you get really deep down in the ocean, the water temperature tends to be uniform. So basically, CO2 levels are higher at depth, the pH is decreased, calcite can dissolve. The depth where all three of these effects manifest themselves mostly, where the calcium carbonate starts to dissolve rapidly. So what are the three factors, right? What I just mentioned, temperature, pH, and pressure. It's called the lysocline. As we get that sharp change. As you go down through this depth, seafloor mud starts to lose its calcium carbonate content. It is less and less calcareous. The depth at which calcium carbonate completely disappears, where its sedimentation is equaled by its dissolution, is the compensation depth. So calcium carbonate now. Now you've heard me talk about temperature. Temperature usually affecting, higher temperature you can dissolve more stuff. Calcium carbonate is a weird one in that lower temperature, but coupled, this is the important thing, it's coupled with the decreased pH and increased pressure, more calcium carbonate will dissolve. So calcite resists dissolution a little better than aragonite. So the compensation depths are slightly different for the two minerals. As far as geologists are concerned, the important thing is where the calcium carbonate disappears, the deeper of the two calcite compensation depth, or CCD, is the significant one. The ACD is shallower than the CCD and is called the aragonite compensation depth. But chemists, chemical oceanographers tend to look at the CCD more so. So a recap here, if I may. So the CCD, calcite compensation depth, is the depth in the ocean below which the rate of supply, calcite, calcium carbonate, lags behind the rate of solvation such that no calcite is preserved. Aragonite compensation depth describes the same behavior in reference to aragonitic carbonates. Aragonite is more soluble than calcite, so the aragonite compensation depth tends to be shallower than the CCD. Calcium carbonate is essentially insoluble in sea surface waters today. Shells of dead calcareous plankton sink into deeper waters are practically unaltered until reaching the lysocline, where the solubility increases dramatically. By the time the CCD is reached, nearly all calcium carbonate has dissolved. According to the chemical equation, calcium carbonate plus carbon dioxide plus water will give you calcium in aqueous form, so calcium ions plus 2 charge, and 2, balancing the equation, 2 bicarbonate ions. By the bicarbonate ions, HCO3, that has a -1 charge, calcium has a +2 charge. So 2 times -1 is -2, with the +2 you get neutrality. Preservations of the ions. But anyway, I wanted to explain to you what is meant by the CCD, so that it helps you understand, I hope, better what is going on as far as organisms who need the calcium carbonate to build their shells, and how with the increasing acidity that the calcium carbonate is more readily going to be dissolving, and this depth at which this is happening is getting shallower and shallower. This does not bode well for food webs and ultimately humans who harvest fish from the ocean. Hope you found this informative. Thank you for your time. Hey friends, this is Jim reminding you to subscribe and share my videos. Also, don't forget to click the bell so that you know when I drop a video in. And I'm also asking for you to please support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your continued support.